Okay, so we'll start the next session, and John will tell us what's new in the Ceph, or with the Ceph file system.
Okay, can you hear me all right? All right. Thanks for coming. I know it's almost lunchtime. I'll try to keep this interesting. So I want to do three things today. I want to talk about distributed file systems and where they fit into the world of storage, why they're hard. I want to introduce the CephFS architecture to you, for those who are not familiar with it. And finally, the purpose of the presentation, I want to give you an update on where we are with CephFS now and what we've been working on recently. So a lot of you probably are not from a storage background, so it's worth defining some terms. Block storage is what most of us are most familiar with in the Linux world. This is when we have a disk in our machine, it appears as dev SDA. That dev SDA is a block device. We also see those in SANs, and we also can have software SANs, where we're using, for example, iSCSI to present something across the network. In Ceph, we provide a block device, but that's not what I'm going to talk about today. Object stores are an important area at the moment, especially in cloud computing, things like Amazon S3 that provide a simplified interface to storage that tends to operate at a higher scale than a typical file system would. And again, we have one of them in Ceph. It's called RGW, RADOS Gateway, but that's not what I'm going to talk about today. And finally, filers, NASes, real file systems, the things we put on top of block devices in a local system. So a local file system would be something like XFS or ext4. And Ceph has one of those as well that operates across the network. And that's what I work on. So within Ceph, we have these three different interfaces to the storage that map to the three types of storage that I've just talked about. And they all sit on the same underlying low-level object store layer. So even our object store interface, RGW, sits on top of another object store, as does the file system and the block device. So in order to talk about file systems, it's worth talking about why they exist, why they want them, and how different they are to the other types of storage. So object storage is the easiest thing to scale out. You can have very simple consistency rules. You're just doing puts and gets, and whoever put most recently is the person whose data is going to appear in the system the next time you read it. Your consistency rules are local to a single object. You don't have to worry about relationships between objects for the most part. So only if one server manages a particular object, he's the only guy who needs to know what's going on with that. Your clients, just doing puts and gets, are usually stateless. Objects don't tend to have aliases. They tend to have just one name. And you can achieve a fairly straightforward scale out of an object store by simply making sure that every object's ID maps to at least one node. Of course, real object stores are much harder and much more complicated than that, but it's comparatively a simple model. File systems, and by file systems I mean POSIX file systems implementing the full semantics that we would expect from a local file system, are much harder to scale out. And they're harder because of the valuable things that they give us. Because they give us a hierarchy. We have relationships between entities, between files and directories. Because they give us the flexibility to alias files, for example, by having hard links. Because they give us permissions models, because they give us metadata like the size of a file and that kind of thing. And because they give us the ability to have smart, stateful clients where you mount a network file system and that client might be doing some caching of both metadata and data. Because of all those cool things we can do with a file system, scaling it out and sharding it is a much harder challenge because it's not just a question of where does a file live, it's where does the file live and where do its hard links live? Where do the parent directories of the file live and where do the parent directories of any hard links to it live? And what happens if you delete a file and it used to live in one place but now its one remaining hard link is somewhere else? And these are the kind of challenges that you have to deal with if you want to build a distributed file system. Final bullet point on that slide about loss of data. Resilience is something we always have to bear in mind in storage systems because users have an expectation that once they've written something, it will still be there when they go to read it back. It's not like if you're developing a piece of software that just lives in memory and you can just reboot it. Storage has to be very robust. And that's challenging in a file system because of the interconnections between objects. If something goes wrong anywhere in the hierarchy, it's not just a local piece of damage to one file or one directory, it's something that potentially ripples through the whole system if you can't walk a tree in the file system anymore. And there's also a subjective thing that's hard about file systems, which is that users' expectations are set by local file systems. They deploy something that operates across thousands of servers, and because it looks like a local file system, they expect it to feel like a local file system. So they have sometimes kind of unreasonable expectations about latency, that you're accessing something from a petabyte-sized pool of data spread across 10,000 hard drives, but they expect it to be able just to do an ls-l on a directory and have all the metadata just appear magically. And so we have some work to do when it comes to things like caching to satisfy the users. And it goes on, because not only do we have to function when every node in the system is up and running, we also have to cope with failures in the system. So if I have a large number of servers that my clients are talking to, what happens when one dies? What happens when a client dies? If the client was holding a file open, can another client come in and open it? How do I decide when the client's dead? What happens if I have so many clients that are accessing so many files at the same time that I exhaust the memory on my metadata servers? And how do I maintain my POSIX semantics in that type of situation? So far, I've just given you a long list of problems, and we'll move on in a moment to talk about the solutions to them. So before we move on, just a quick terminology thing. Hopefully most of the people in the audience will be familiar with these terms, but a file generally corresponds to an inode in a file system. If you have hard links, they might point to the same inode. A dentry is a name for a file within a directory. A directory is a special type of inode that can have a bunch of child dentries. And a hard link is where you have multiple dentries pointing to the same inode. These terms make a lot of sense in a local file system, and if anyone here works on local file systems, you'll have a typical idea of how they fit together on disk. But when you map them to a distributed system in a network file system, you keep the concepts because that's the interface that the client expects, but the way you store them on disk might be a little different. So, CephFS came into being some 10 years ago via Sage, who's in the audience here. There's a reference to the paper at the bottom of here, and the point of referencing that is that this started out as an academic project to try and solve the metadata problem that large government labs were having with large file systems on supercomputers. Ceph and CephFS were originally the same thing, but over time, the underlying object store within Ceph started to be used for other things like block devices and the RADOS gateway. And those, in the days of Inktank, which is the startup that redhat acquired, were commercially more readily able to be provided. So the file system took a backseat temporarily. But it's still pretty interesting to work on, and there are several developers working on it now to try and get it up to speed. And the reason it's worth getting it up to speed is because of these features. So we dynamically scale out metadata, and that's something that very few network file systems can actually do well. It's a hard thing to do because you have to decide how you're going to do it, and I'll go into that in a second. CephFS takes almost a shortcut for data storage in that we have this underlying object store called RADOS. I'm not going to explain how RADOS works in this presentation, but it is very scalable and very resilient and fairly performant as well. So unlike a file system like ext4, where we're asking how to store files on a block device, in CephFS, we skip that whole block device aspect entirely, and we're just asking how do we map a POSIX file system interface to the underlying object store. We provide POSIX compatibility, which not all network file systems do. That means that if you developed and debugged a user space application on top of a local file system, the chances are you can pick it up and run it on Ceph FS, and it'll behave exactly the same way. And we even go a little bit beyond the POSIX specs, so things that many local file systems don't have, like snapshots and recursive statistics that allow you to see how many files and bytes are in a directory without having to traverse it from user space. So the important parts of any network file system are the client and the server. In the case of CephFS, the client can be our Fuse client or the kernel client, which is in the upstream Linux kernel. The user space client also shares a lot of code with something called libCephFS. So if you want to talk to a CephFS file system without actually mounting it from the operating system's point of view, you can link to libCephFS and do things like opens and reads and writes that way. The server we call the MDS, that's the metadata server, and you can have more than one of those. And the MDSs sit on top of RADOS that provides the underlying storage. So that's that in a diagram form. In this one, the kernel client is in use. And the key thing about this diagram is that the data path and the metadata path are separate. So the data operations are going to OSD servers, which are within the Ceph RADOS object store. So they're going directly to this backing store, which is unaware that it's a file system at all. And the metadata operations are going to our MDSs. And that separation is important because it means that we can scale metadata and data storage independently. That's yet another picture of the same thing. So your application goes through one of our many clients. There is a network protocol that's unique to Ceph between the clients and the servers. And that network protocol will either go directly to an MDS for metadata operations or to the RADOS store for data. What's interesting about this is that the MDS also uses RADOS. So the metadata servers in Ceph don't use their local disks at all. They go straight through to RADOS. And any access to an underlying disk is going through RADOS. So if we want to distribute metadata, how might we do it? The simplest thing is statically identify some directories you want to be served by one server, some directories by another server, and assign them and get on with your life. That's fine for some use cases, but it's not a general purpose solution because it relies on the administrator to predict how end users will use a system. And particularly at large scale, the system administrators are often different people from the application developers. They don't know what's going to happen in what folder or how it's going to be used. So that doesn't get you too far in some environments. You can take the hash of a file system path and use that to decide which server a particular file should go on. And that is a workable approach, but it has some shortcomings. Most notably that if you have a large number of files in a directory, then they would all have a different hash for their path, and you would map them to different servers. So in this case where a user naively decides they want to run ls-l on a 10,000 file folder, they might find that had to go out and talk to 1,000 servers to do that, which is fine up to a certain point in scale, but when you get to very high scale systems, that becomes an issue. So the third bullet point there, dynamic subtree partitioning, is what CephFS does. So rather than assigning on a file-by-file basis to different metadata servers, we identify subtrees within the overall file system hierarchy and assign those to particular metadata servers. And that's a visual representation of what we're doing. So the overall tree there would be all the files and directories in your file system, and we're identifying subtrees and subtrees within subtrees as interesting units of distribution. So think of each of those different colored blobs as a shard. And we are able to individually assign those shards to different MDSs. And this is a kind of best of both worlds situation, because we get that splitting of the metadata, we get the ability to balance it across metadata servers, but we're doing it at a semantically meaningful level. So we're doing it in a way that the user expectation that when they go list a directory, that's going to go look at one server or a small number of servers, is embodied in this model.
So this is done automatically for the servers to talk to each other and decide where?
The servers maintain a heat metric for different directories that they're serving. And they periodically get together and do a global exchange of their heat data, and then make a symmetric decision about, as a result of that, who should have which folder. In typical use cases, you don't necessarily need to do that rebalancing that aggressively, because once somebody has deployed their applications on a system, it's really more of kind of at most every few minutes you might have a significant shift. But CephFS will go a lot faster than that. It will rebalance much more aggressively if it thinks it needs to. But that act of actually making the decision about where's hot and where's not is something that we can afford to do in a fairly global way because we do it periodically. So in addition to having the locality of having a directory or a subtree on a single MDS, we get some extra advantages from this approach that we can replicate subtrees. So in addition to deciding who should be serving the authoritative copy of a subtree, we can replicate that metadata to other MDSs as well. And that's very important in a read-heavy workload. So if you've got a great big tree of data and all your clients are trying to enumerate files and directories or just read files, you don't want that to cause a hotspot. And so we can avoid that by replicating the data out to multiple MDSs, and then the clients can just make a round-robin choice of which MDS shall I ask for my metadata today. And finally, the observant reader will notice that even though we can shard subtrees around, that doesn't help you if you've got a huge monolithic directory. So in actual fact, what we work with are directory fragments, which are hashed entry names within a folder. So we have these little fragmented data structures within a folder, and all of our distribution code actually works with these fragments rather than with directories. But for the most part, when I say directory, assume I mean fragment, and that gets us around the issue of very large directories. So I'm going to briefly touch on the data placement as well as the metadata placement. This isn't something CephFS itself has to worry a lot about because we're using the RADOS object store. But we do have to decide how to use RADOS. So it's a very simple scheme that we have. We just take the data in the file and we stripe it across objects. By default, 4 megabyte chunks linearly, but there's a bunch of customization you can do with that if you want to. So you can do sort of, you can do write the first megabyte to one object, second to another object, third to a third object, and then the fourth back to the first object, and that kind of thing. But most people will be perfectly fine with just dividing things up into 4 mega objects. That scheme makes us fairly tolerant of bad things happening to the objects beneath us. So if something does happen to one of the objects that was in one of the files, the user would find out about that via their underlying RADOS store if something bad had happened, which it shouldn't, but we have to live with the possibility. And we can simply return zeros if an object isn't there. Now, that is not a normal use situation, but it's something that for disastrous situations we have to think about. And if you do want to change the striping on a particular file because 4 meg chunks isn't working for you, you can do that generically from user space by setting some magic exatras on the clients. And it's worth noting that the data is all going from the clients to RADOS. I know I've already said that a couple of times, but it's important. It's not going through the metadata servers, with one exception, that is deletions. So when a client wants to delete a file, that's a very quick operation from the client. It just tells the metadata server, unlink this file, and then the metadata server will ultimately, at some point in the background, delete the underlying objects for the file. So I've mentioned the different clients we have. It's worth talking a little bit about what the differences between them are. So other than one is in user space and one is in kernel space, you will notice differences between how they perform, especially that they're using different caches. The one in the kernel is using the Linux page cache, and the one in user space is using something called the object cache, which is part of Ceph. You might not care. Client performance might not matter very much for you if you've just got a very large number of clients. But if you have a small number of clients or just one client, then client performance is going to be very relevant to you. So you might be interested in trying the different clients. The MDS uses a journal. The interesting thing about that within CephFS is that we're not just using the journal for resilience. We keep the journal for longer than we would usually need to, so that when an MDS restarts or another server takes on the role of an MDS that has failed, we replay that journal and we get ourselves a hot cache by doing that. So the MDSs will most of the time keep most of the metadata in memory, and the journal is one of the ways we achieve that. We're able to have a very big journal because it's all going into the underlying RADOS object store, which is typically very large indeed. So that assumption that most of the metadata is in memory most of the time, of course, is workload dependent. If you are just creating lots and lots of files, then you would not get the benefit of that. So there is some kind of user tuning that you might need to do in that situation. In addition to the typical use case, where we're going and getting a file by listing it in a directory or traversing its path, which is how our data on disk is laid out, sometimes we need to go the other direction. We need to go from an inode to a path. And the only mainstream use case for this is NFS, because NFS keeps file handles on a client, and sometimes it'll come back to a server and say, hey, remember that inode I opened? And usually the server would actually not know. No, I don't know that inode. You have to tell me the path. So that's handled in CephFS by actually storing a tiny bit of metadata in the data pool. So because the striped data objects for a file are named after its inode, we can look them up by inode. So the metadata server also puts a little bit of data on those, called a backtrace, that allows us to look up by inode when we have to. And this, for the most part, is kind of an annoying thing. We've got metadata going into the data pool. We're having to do extra writes. But it's a necessary thing for handling the case of lookup by inode. And it also gives us a nice bonus, which is that if, for any reason, something happened to the metadata pool, we would be able to, in many cases, go and reconstruct a rough impression of what the hierarchy was by looking at the backtraces in the data pool. So what does it actually look like to create a CephFS file system, having talked at a very high level about what it is and why it's great? Well, it's actually surprisingly simple. If you've got a Ceph cluster installed and you're using our Ceph deploy tool, which is the simplest way to set up a small cluster, you type mds create and tell it a server, and it'll go and set up a daemon running on that server. You create some OSD pools, which is what the metadata server and the clients are going to use to store their data. And finally, you tell Ceph that you would like to enable the file system using the fsnew command. And you tell it which pools you'd like to use. Initially, you just give it one data pool. You can give it multiple data pools in the future if you wish to, and you can assign based on directory in the same layout structure where we configure striping, you can configure which pool you want it to go to. So for example, if you want to put one directory on SSDs, and another directory on spinning disks, you can achieve that by creating different RADOS pools in the underlying storage and then passing those through to CephFS. And then finally, in this example, I'm using the kernel client, I go mount it on another server somewhere. And the XXXX is just an IP address. And that's the IP address of one of the Ceph monitor servers, which are servers that handle the configuration and state of the system. So that's all you have to tell the client to get the file system mounted is, here's the IP address of one of the Ceph monitors. And I haven't shown it here, but there is also an authentication key that you would pass there as well. It's not a free-for-all. You do have to be authorized to access the file system. Clients are more important than people first realize in terms of something that you have to be aware of and manage in your Ceph cluster. So this is kind of general user advice for anyone interested in deploying and testing CephFS, that people will often say, my cluster is stuck, or something like that, and assume that it means something is wrong with the server. And a lot more often, it's actually something has gone wrong with a client that's holding some resources. So the operation of evicting a client in that type of situation can be quite important. And I'll say a little bit more about that later. So if you do want to deploy CephFS to evaluate it, to play with it, to hack on it, ideally you want an MDS with a lot of RAM. Something seems like it's going wrong, look at the clients, not just the servers. Use recent code. CephFS is under heavy development, and if you're going to use the kernel client, use a recent kernel. And currently we have this conservative configuration that we're recommending people use, where they have a single MDS, and they don't use the snapshot feature. So that model of the dynamic distribution of data and multiple MDSs and that kind of thing, that code is all in there, but we are partway through the process of testing and making robust all of this code. So we're kind of having to pick our battles, and we haven't had the multi-MDS QA battle yet. So if you want the maximum chance of your system staying up, then you would run a single MDS. It's worth saying, though, that most of the bugs that we find, in fact, pretty much all the bugs that we find, are not data loss bugs. We'll hit assertions in our code from time to time. We might have a crash from time to time. But bugs that actually lose user data are exceedingly rare. Okay. So the last and most interesting, perhaps, part of the presentation is what we're actually doing to get this wonderful vision into the hands of users. So our focus is entirely on resilience, because that is the primary thing that anybody cares about from their storage system. If you didn't mind losing the data, you wouldn't be writing it to disk to begin with. So that's the most important thing. And that means we don't want to corrupt user data. That's the most important thing. The second most important thing is availability. We need to not crash. The third most important thing is that we need to not crash even when something very rare happens. So at the moment, as long as people stay pretty much on the beaten path of normal file system use, they're relatively unlikely to see any issues, but there are certain corner cases around hard links and deletion and that kind of thing that we need to handle. And when something goes wrong, we have to tell people. One of the flaws in a lot of distributed file systems and network file systems generally is that when there is an issue, it's super hard to work out what went wrong. You have things like typing mount and having it just hang, typing ls in a directory and having it just hang. And what are you supposed to do when that happens? So in order to provide people with the ability to investigate and handle situations like that, we have to write a bunch of code. We have to add explicit sanity checks at a bunch of levels in the system that say things like, if we asked a client to relinquish some lock, and it hasn't, then rather than having something just hang, we can actually fire up an alert to the user. And as we add all these things, we need to add tests that go with them, which is terribly boring, but terribly necessary as well. So this is a quick list of the things that we've been working on. I'm going to skip that and just go through them directly. So recovering from damage in a file system, if I go in and delete or corrupt one of my underlying RADOS objects in the store, that's something that shouldn't happen. RADOS is supposed to be taking care of that for us, but we have to handle the possibility that it does. And in order to do that, we have to continuously verify this data. It's not just about FSCK, it's about scrubbing, so that you find out as soon as something's gone wrong. And we also have to do that online just because of the way the system works. If you tried to shut off a multi-MDS Ceph file system and check the consistency of everything that was on disk, you would have to re-implement all of the peer-to-peer protocol in order to make sense of what was on disk at any given moment. So this stuff all has to be online. And then finally, there's repair stuff, which can happen offline. If something truly disastrous has happened, like your metadata journal has been corrupted, then we need offline tools for that. So at the moment, the online scrubbing functionality is something that you have to invoke directly by hand using a diagnostic command line. So this is the primitive out of which scrub will be built. And that's what it looks like if you invoke it. You tell it a path that you want it to check, and it'll go check it by traversing the whole metadata tree and going and comparing what it finds in memory with what's on disk and checking that the statistics all match up. So if the parent says it has 4 folders, that there really are 4 folders. And it'll tell you yes or no. And thankfully, in this case, it's telling us yes. There'll be a lot more detail about how this works in a talk that my colleague Greg is giving at Vault. And if you're not going to Vault and you're interested in open source storage, then I recommend you do. So I talked about the importance of knowing about what your clients are doing because they're often a source of problems. Clients, as they connect to us, are fairly anonymous things. They're just an IP address which happen to have the correct key connected to us. But we would in general like to know more about clients. So we've added some hooks to gather more metadata. So currently it's simple stuff like the mount path and the host name, but there is scope to make that more interesting depending on application use cases. So if you are running in, for example, a Hadoop or an MPI environment, you might want to take your job ID and associate that with the clients so that if someone on the server side could see that something was going wrong with the system, they might just boot out all the clients associated with that. And that'll become a lot easier if we can add explicit identifiers based on the application. And currently, eviction works. It's a little bit clunky at the moment if you want to do it completely thoroughly, because if you decide that you truly don't trust a client, you can't just kill its connection to the MDS. You have to blacklist it with the RADOS cluster. That's the OSD blacklist command. So prevent it writing any more data. This is what in a storage environment you often call fencing. Then we can evict its metadata session, so the MDS will no longer talk to it. And finally, we actually have to barrier the whole system, not synchronously, but we have to ensure that they don't do any more I/O until they've seen the version of the Ceph data structure called the OSD map, which reflects the blacklisting of that client. So that might not make that much sense if you're not from a storage or distributed systems background, but the key takeaway there is that the current state of the code is that you can robustly blacklist things, but it's just a little bit clunky and you have to know these magic commands. So in future, we'll be looking to wrap that up and make it more straightforward to for people to use. So I talked about the kind of, there's a question? So the question is, how do you get a client back after you've evicted it? Rebooting is sometimes the simplest way. Nothing. So when you evict a... Okay, so the blacklist operation affects a particular instantiation of a client, not the client's IP address. So it's kill this client process, not this client host.
Just a suggestion, you might want to think about as goal remounting as opposed to rebooting would be a good goal.
Right, so I mean, rebooting is obviously the worst case. In many cases, especially if you're using a user space client, you might be able to do something softer. You also don't have to go through that whole process. If you know what your clients are doing, and you more or less trust that they're not going to try and flush bad data anywhere, you can skip the blacklisting part, and you can just evict the metadata session. And that's like a kind of a soft eviction. So, for example, if you have a client and you know nobody else was trying to access the same files that client was accessing, then you would do it like that. So we'd want to make sure users had both options. The actual blacklist part is the nuclear option, and the pure metadata eviction is more of a, I'm comfortable that I understand what's going on, but I would like to evict this session anyway.
It might be worth noting that the eviction happens automatically in the client code, you don't actually understand.
Right, the soft eviction happens automatically. The really aggressive, kick this guy out completely is something that's a by-hand thing. Okay. And in addition to the sort of explicit state of the system health checks where we're firing off automatic alerts, we're all the time adding interesting little extra tools. So this is just this week. Anyone who uses dstat will find this very familiar. Something that will let you look at what's going on an MDS. And you have to have a fair bit of knowledge to understand what these numbers mean. But if you do understand what they mean, it's very instructive. So I can see in my stry column, my strays, I can see how many files are queued up to be purged because they've been deleted from a client, but the objects haven't been deleted yet. That's quite an interesting queue if you're having a problem with your system and it seems to be running slowly. I can see, second to right, how many journal events are getting written. So I can get a general sense of how active the client is. And even if you don't have a deep understanding of this kind of stuff, just seeing that a number is 0 or not can be very instructive if you're trying to work out, is my problem with my MDS? Is it with my clients? What is it? And there are lots of other new commands landing all the time that let you dump interesting things about the state of the system. So we recently changed the format of the metadata journal to add some special bytes that will allow us to find the events if something gets corrupted, so that we don't have to be able to follow the journal all the way through. If you lose something halfway through, we can go find the magic bytes and use that to recover something. There are some tools that go with that. Resource limits are a challenging thing, especially if you start running out of RAM and you've got stuff cached on the MDS. You can't necessarily flush the cache if clients are actively using it, so you need this communication between clients and servers to instruct the clients to evict data. And that's something that has existed for a long time, but has only become robust and tested comparatively recently. And there is still, as we look at performance at some point in the future, there will probably be opportunities to do smarter things than we currently do in that area. Handling full space is something that we changed quite a bit recently. So the underlying RADOS store will just start blocking your operations if you run out of space, because it doesn't want to accept any writes that it can't safely replicate. So the problem with that is that because we use the RADOS object store for our metadata, including our journal, we can't do a delete without doing a write to the journal. So we have a solution to that, which is that the MDS is exempt from this rule that you can't do writes when the cluster appears to be almost full. And we've recently added some code around that, which allows the client to deal with that sensibly and avoid certain deadlocks that could have otherwise occurred. We have been writing lots of tests, and we also started using CephFS internally on our test cluster for storing all of our test results. Within the tests that we run, there's kind of a variety of things. Historically, we've had a lot of client workloads, the same kind of test you might use on any file system to verify that it's functioning correctly. In addition, some Ceph-specific thrashing code that will do interesting things like crashing servers and checking the system copes. More recently, we've been adding a lot more functional tests, which are these more complicated Python things that verify a lot of the clever internal bits, and it wouldn't be obvious that something was going wrong without hooking in and looking internally at the state of the system. So checking. The simplest example is when you delete a file, are the objects in RADOS actually getting deleted, which is not at all obvious if you're just a client. And it turns out that was actually broken in some cases until the point we actually wrote tests for that. Our priorities going forward are entirely guided by what the community wants. Recent feedback has indicated multi-MDS quotas, and the community shares our priority of having recovery tools in FSCK. And finally, here are some links for anyone who wants to get involved. And if you are trying it out and finding issues, some pointers about the kind of things that might be interesting to tell us or to try out yourself. So that's all I have. I've only got 2 minutes for questions, so any questions? Yes? Is your module in the kernel or kernel app? Yeah, the kernel module is upstream. Yeah, has been for some time. Yes? I'm sorry, I didn't catch that. Yeah, so split brain can't happen in Ceph. I didn't explain the RADOS layer in detail, but part of that is a odd-numbered Paxos cluster of so-called monitor servers that will ensure that none of the system state gets updated unless you have a quorum of servers there. So split brain doesn't happen. Any more? Well, when I talk about Ceph, I'm talking about the Git master. So a more serious answer to that. So the question was, what version am I talking about when I talk about all this stuff? So CephFS is an upstream piece of development. In the Red Hat jargon of upstream, downstream, there is a downstream Ceph product that includes the block device and the object store interfaces, and the file system work is currently happening upstream. So in terms of what version of the downstream product is the file system in, it isn't. But there are versioned, tested releases of the upstream software as well, and it is in whatever the most recent stable version you download is. But in general, if you want to use the file system, you would probably want to live a little bit more dangerously than a normal user in terms of having the most recent version you can to get all the FS bug fixes. Oh. Okay. The question is, what are the use cases, and would you use it for storing virtual machine images? So if you have VM images that you want to store on Ceph, you would do that using the block device interface rather than the file system interface. And there are existing hooks for that to operate with libvirt, QEMU, that kind of thing. For Ceph generally, using it for the block devices in, for example, an OpenStack cluster is the typical use case. And we don't have any end-user work use cases for the most part for CephFS because it's not something end users are using mostly. But those who are, and there are some of them, unsupported people who like to live dangerously, are mostly, I believe, using it in technical environments. Thank you very much. I'm out of time.